Soren Eilers, who's going to talk about operator norm stability of virtually Abelian groups.
Thank you, and thanks to the organizers. It's been a wonderful week this far. So I decided to make this talk maybe a little bit too C-star algebraic, so I hope I can get away with this. So there are some very strong connections that you've seen in several talks, Marius, for instance, this morning, which are directly related to the kind of stability that we're talking about in this conference, but only about matrices, unitary matrices with the operator norm. So that is in the title. So for a reason that will become obvious in a second, I can only say something about operator norms. And that's because it's sort of built into my methodology that the norms I can work with are operator norms. But I want to look at, and also as Marius points out, this is not so easy to get stability in operator norm. There's not so many examples. And so you may be surprised that I want to do something even stronger. So I want to do even stronger types of stability in what's going to be more general C-star algebras in a moment. But so I've decided to sort of do this fully, but I realize many of you are not used to these kinds of problems, so I'll try to go slow, and please stop me if I don't. So I want to talk a little bit about C-star algebras. I'm going to flash this. This is the definition of a C-star algebra. This is a little bit unfair because if you haven't seen it before, it's not going to help you very much, right? But a C-star algebra is, first of all, it's a complex C-star algebra. This is very important. It's a Banach algebra. So that means that it's a Banach space that's also a ring, and the norm is submultiplicative, like this over there. And then it comes with an involution, so that's the star of the C star. And an involution is a conjugate linear map, which sort of, you do it twice, you're back again, and it reverses the order of the multiplication. Right, so this doesn't help you very much, right? But these are the axioms, and I will talk a lot about star homomorphisms, and this just means structure-preserving morphisms, so maps that sort of takes everything to elements, products to products and so on. You actually can prove it's automatic that if you have things that respect all the algebraic structure, they will be norm decreasing, so you don't have to ask about continuity. So importantly, and this is sort of, I want to show you how we work, right? And to show you how we work, more than just showing you C-star algebras, I think it's very important to show you the basic constructions of C-star algebras. So there's many ways of making sort of new C-star algebras from old. So let me just go through them. They're not very surprising, but this is somehow key in the proofs that are behind what I want to show you. So first of all, if I have a C-star algebra and I have a closed star subalgebra, then that in itself is a C-star algebra. It's easy to see. If I have like an increasing chain of these in a C-star algebra, then I can take the union and I need to close it off, and that will be a C-star algebra. I need to close it off because it has to be complete. There's also a quotient construction, so if I have a closed two-sided ideal, it will first automatically be closed under the involution, and there's a way of putting a norm on the product. You can do direct sums. You take the max of these two norms, right? So it's like an infinity norm. And if you have infinitely many, there's at least two things you can do. You can do the product or the sum, right? And the idea in the product is I just take infinite tuples of elements in all the C-star algebras, but I have to require that the norms of the individual elements is bounded by some universal constant, and then the norm of that will just be the soup of these norms. That will work, but you can also take I would call this the product, and then the sum is where I require the norms to go to 0. This will also give you a C-star algebra. And finally, this is a somewhat different kind of construction. You can also, whenever you have a C-star algebra, there's a way of putting a norm on the matrices so that you get a C-star algebra. So some of these things are a little bit hard to show, some are straightforward. I'm not going to discuss which is which. But now I'm going to show you two classes of examples, right? And I think this is the right way of thinking about C-star algebras, not this sort of list of actions. C of x, where x is a compact Hausdorff space, is a C-star algebra. So I'm just using the pointwise operations, and the star is the pointwise complex conjugation, and the sup norm, and also the matrices, the complex matrices. Right? And it's very important here that the norm that I'm putting on the complex matrices will be the operator norm, and you can prove that this is the only norm that you can put on this algebra, making it into a C-star algebra. Right? So if you have a into a C-star algebra. So to satisfy, there's many ways of making it into a Banach algebra. You just need a submultiplicative norm. But if you want it to preserve, oh, did I forget the key action? I did? Oh, okay. So,
The top.
oh no, it's top. Okay, I didn't. Okay, so the C-star identity, this will force, actually the way it works is that it will force the norm of x star x to be the spectral radius, and the spectral radius is an entirely algebraic concept. So you can sort of see that this topological norm concept is completely described by the algebra, so this is why it's unique. So, so that's why I only know how to talk about operator norms, because if it's a C-star algebra, and it sort of has to be a C-star algebra for me to be able to do anything with it, I need the operator norm. And then of course there's these important results that, you know, by Gelfand, and I don't know exactly who did the C-star version, but it's kind of a Wedderburn type result. So if you have any commutative and unital C-star algebra, it's C of x. And if you have any finite dimensional C-star algebra, it is of this form, right? And I'm using my constructions from before, right? I take maybe, I could start with C, which is the continuous functions on a point, then I take the matrices, and then I add them up. So this is sort of what they look like. There's another way of telling people what C-star algebras are. This is quite common, but using the so-called GNS representation, it's easy to see that B of H is a C-star algebra, the star is the adjoint, as you would expect. And then you can prove that any C-star algebra sits inside a B of H as a sub-algebra in my first construction from that slide. So I'm just going to introduce...
H is always Hilbert.
It's a Hilbert space, yes. So H is always a Hilbert space, and always a complex Hilbert space. And so a star homomorphism is, if I have a star homomorphism from an abstract C-star algebra into B of H, those are very important. We call them representations. And then the famous result by Gelfand, Heimek, and Siegel, the GNS result, says that whenever I have a C-star algebra, any C-star algebra, I can find an injective representation into some B of H. Right? So you might as well, so of course A is isomorphic to its image inside B of H, so any C-star algebra is a sub-C-star algebra of B of H. Right? So your definition could have been that a C-star algebra is a sub-algebra of B of H, but that's not a very reasonable definition, because very often you don't care about the B of H, right? You just want to work with this abstractly. And for later use, let me introduce some notation. There's something called an irreducible representation. This just means that there's nothing that commutes with all the elements in the image, except of course the scalars. And you should think of an irreducible representation. I mean, you know this kind of object. So any representation can, in a certain sense, be constructed from irreducible representation. You sort of integrate them together, right? So these are sort of the minimal ones. Okay, so that was C-star algebras. Now some groups. There is, and this is the same construction that Marius was describing this morning. So there is the group C-star algebra. So I'm going to make my groups discrete and countable. That's not entirely necessary, but that's all I know something about here. So of course I can represent a group into a C-star algebra using the group of unitaries. Right? So if I have a group homomorphism from G into the unitaries of A, that's a representation of the group. And then what you can do, and there's sort of two different ways of doing this, and we've seen both. So I'm going to use the same way of thinking about it as Marius did. It's like a universal object. So it says that there is a C-star algebra. For any G, there's a C-star algebra that I'm calling C-star G, so that whenever I have a representation of G into the unitaries of A has to have a unit for that to make sense. Right? Then I can factor it through the universal object using a star homomorphism. But you can also describe this as the group ring where you sort of close it off in an appropriate topology. And this is what Kristen showed us a few days ago. So that's the same. Okay. Now, as I said, I want to talk about very specialized and restrictive, strong types of stability, but I'm only going to do it for very sort of relatively simple-minded groups. The groups I want to talk about will be virtually abelian, and actually quite a lot of the time they will be abelian. Right? So it's fairly easy to see if you use just the Gelfand result that I mentioned already and combine it with standard sort of Pontryagin duality, that G is abelian if and only if C star G is commutative. And so any commutative C star algebra is C of some space, and the space is just the dual space, right? The Pontryagin dual. So this works out very nicely. And then there's a surprisingly old result by Thomas, mid-60s, I think, early 60s, realizing that G is virtually abelian if and only if C star G is what's called subhomogeneous. And being subhomogeneous just means that if a C star algebra is subhomogeneous, that means that all the irreducible representations end up in a Hilbert space of a bounded size. Right? So if you have an abelian C star algebra, an irreducible representation of a commutative C star algebra is of course one-dimensional. Right? So this is sort of an easy way of generalizing commutativity. And you can very easily see that if you have a subalgebra of the matrices of C of X, they will be subhomogeneous. But this is not all of them. Right? This is something you would call like globally trivial, but you could have more sort of a gluing thing going on. So there's many more subhomogeneous C star algebras than those that sit inside here. Okay, so now I have at least a little bit of a connection, right? So I have groups. The groups give me C star algebras, and these C star algebras are sometimes commutative, sometimes subhomogeneous. So this is what I want to talk about. Okay, so now I'm starting over a little bit, and I want to show you some lifting properties that have been studied for C star algebras for quite a long time. In a sense, the first time it was formulated was in the first half of the 1980s by Blackadar, and actually there's a competing notion by Efros and Kaminger. But this is the one that I'm going to work with, which is called semi-projective. And it's as you can see, it's sort of a lifting property. So this dotted arrow is supposed to mean there exists, right? So the way this works is that I will say that A is semi-projective, so A is the C star algebra. If whenever there's a map, a star homomorphism from A into something that looks like this, then I can lift it. But I need to go through the construction here, right? So I'm saying I have a B, and this B has a nested sequence of ideals. Right? So inside B there is I1, which is an ideal of I2, which is an ideal of I3, and so on, and they're all ideals of A. And so I can take the union of these, as I mentioned before, close it off, and that gives me an ideal. Right? So now I have this quotient C star algebra, and now I may have a star homomorphism that goes to here. And then the semi-projectivity condition is that I can lift any map of this kind, but I'm not requiring that I lift it all the way up to B. I'm just requiring that I can lift it to some level. And this may look a little bit strange. A place where you may have seen this before is the concept of an absolute neighborhood retract in topology. And actually it turns out that if you translate this, if you take A to be C of X, and you make the additional restriction that B and hence the i's are commutative, that's exactly what you get. Right? But I want to do this with non-commutative targets, even though I have a commutative source. Right? So even if A is commutative, these may be non-commutative.
So that's again, that will, if in the commutative case, then what will be a retract of what?
So C of X is semi-projective if and only if it's an A and R. It's an absolute, an absolute neighborhood retract. And if you sort of translate what does it mean to be an absolute neighborhood retract, and you sort of dualize everything, this is precisely what you can do, but only for the targets that are also commutative, so coming from spaces. Right? So it's like you take X, you put it inside, and there it has to be, whenever you have, there has to be a neighborhood that retracts back. So this is the concept. So there is also a concept of weak semi-productivity, and this is where the notation gets a little bit iffy, because compared to the kind of weak stability that we've talked about, this is much, much stronger. But it's called weak semi-productivity. I can't really change that. So you're going to have to live with that. It's the same kind of lifting property, but it is for a very special situation where I have product modulo sum. So if I have a star homomorphism into a product modulo sum, the condition is I need to be able to lift it to the products. And I could do this restricting to the special case where all my B's were finite dimension, or let's just say matrix algebras, and then this is the matricially semi-projective concept, right? And this is where it becomes a little bit familiar again. We've seen these kinds of lifting properties in several talks, for instance in Gunnar, the very first talk, that somehow this is a translation of stability. It's this kind of lifting property is what you want to do when you study stability in matrices. Right. So I have these key observations. So semi-productivity implies weak semi-productivity implies matricial semi-productivity. So let me just go back and explain why that is. Right. It's obvious that if I have weak semi-productivity, this is for all B's. So if I can do it for all B's, I can also do it for the matrix algebras. The other condition is a little bit less clear, so I want to convince you that if I know this, I know that, right? So the idea is that, so combining these things, so the B that I would have over here would be the product of all the BI's, too many B's. The I would be the sum of all the BI's, and the IN, so this is from 1 to infinity, the IN would be the sum from 1 to n of BI. Right? So the point is that these INs grow up to be this thing here, they increase to be that, and so the assumption is that I can lift not the whole way, right, but up to B modulo IN. But what is B modulo IN? Well, B modulo IN will just be the sum from n plus 1 to infinity of BI. So this is sort of, if I know semi-productivity, I don't really get this, right? I just get the map, I get the lift to here. But then it's easy to see you can just pad with zeros and you'll get the same target because when you mod out by this anyway, it doesn't matter. So that's why semi-productivity is stronger than weak semi-productive, which of course it should be. Okay? And then if you sort of sit down and translate, matricial semi-productivity is precisely the kind of stability that we're talking about here, but of course only for the operator norm. I'm going to talk about groups that are not necessarily finitely generated, and that is not really a problem for me, right? It's not really a problem for these lifting type of questions, but it is a sort of a sticky point to understand what it means to be stable when your groups are not finitely generated. But if you know what that is, it's going to be the right thing. What is then weak semi-productivity? Well, it's stability in the sense that we've talked about throughout the week, but in a general Caesar algebra, right? So it means the kind of, for all epsilon, there's a delta, so that if I have a representation into the, I have a delta representation into the unitaries of a general C-star algebra A, then without moving it more than epsilon, I can find an exact representation. And the point here is that, you know, for all epsilon there is a delta. This has to be uniform in all C-star algebras, right? So it used to be uniform in all matrix sizes, but now it's uniform in all C-star algebras. So this is why this is perhaps not a very common thing, but I'm going to show you some examples. Semi-projectivity, the full thing, translates to stability fixing exact quotient representation. I want to draw this for you. I'm sort of hoping maybe it looks familiar to some of you guys, but it's not something that you see for unitaries for unitaries in matrices, because the matrices are simple. So it's not something that. But the whole idea is that, you know, here I have C star. Here I have G, right? And what am I talking about? I'm talking about the situation where I'm representing G into U of A, and this is an almost representation, right? And then stability means that close to it there's a real representation, so that, you know, the difference is not too big. This is what it means to be stable. So what does it mean to be this extra condition of fixing exact quotients? Well, the idea is that suppose that I have an ideal inside A, and then I sort of continue on to A mod I with the map induced by the quotient map. And suppose that I know that when I take this almost representation and go down, the induced map, right, so I'm going to call this gamma, the induced map kappa composed with gamma is in fact already exact. Right? So suppose that the problem that made this not exact goes away when I pass to the quotient. Then the added restriction is that when I make this perturbation to something which is an honest representation, then I cannot change what happens here. Right? So I need to fix. So I'm in a situation where I have an almost representation that in the quotient becomes exact. Then the rule is that when I fix the almostness and get it to be an exact representation, I'm not allowed to move what goes down here.
Right. So just to make sure I understand, so is this the same as saying that if the errors are in an ideal, then you can make the corrections inside the same ideal?
Yes. Okay, so oops, wrong button. If I can make this go away. Yes. Okay, so I mean, the very ambitious goal is to figure out, you know, for what groups are the group C-star algebras semi-projective, weakly semi-projective, or matricially semi-projective. And I don't know how to do that, right? I'm just going to show you some examples. Sometimes I will say that the G itself is semi-projective, weakly semi-projective, matricially semi-projective. And there's really only one really general result that we have, and that is that if this is something I did with Tatjana and with Adam Sorensen, who is a former student of mine. So if we have a finitely generated and virtually free group, then the group C-star algebra is semi-projective. So the strongest property comes from this way, and I mean, in a way, I'm sort of proud of this, but in a way, it's not so surprising because you know, if you have something that's finitely generated and free, it's easy to see, and then you can sort of, if you know it looks like this, there's like an H&N extension. If you're careful, you can lift things and so on. This might be if and only if, as far as I know, but that's a hard question. Okay, so this was the setup. Now let's go through the Abelian and virtually Abelian groups, and I'm going to tell you all that I know about this. So the history of this is that this is something that I started looking at without knowing that I was doing group C-star algebras in the late 90s with my former advisor, Gil Peterson, and Terry Loring. We didn't think about groups at the time, and then, but we were actually doing something I'm going to show you in a second. Then more recently, I don't know, is that 8 years ago or something, and, we started talking with Adam about this, and we sort of really did this project, and then we realized that we could actually say something about some groups, for instance, crystallographic groups. And then more recently, there has been developments in understanding these sister algebraic concepts, and I want to sort of try to apply those. So this is somehow the history. So it's a long story for me. Okay, so if you want to know when a commutative and unital sister algebra is semi-projective, weakly semi-projective, matricially semi-projective, it's almost known. Right, so there's a little snag in this last result here that I'm going to complain a little bit about, right? But Sorensen and Thiel proved that C of x is semi-projective precisely if x is an absolute neighborhood retract of dimension, and covering dimension less than or equal to 1. Right, so it's necessary to be an ANR because you have to, if you test against commutative targets, that it needs to be an ANR. And it's not enough to be an ANR, you need to be no more than one-dimensional. So a good example of something meeting these assumptions would of course be the circle, right? So this means that Z, the group Z, which has the dual the circle, is semi-projective. Right? That's easy to see without this. Weak semi-projectivity becomes ANR, so there's something called an approximate absolute neighborhood retract. So I mean, so the idea of an absolute neighborhood retract is your space. Wherever you embed it, there has to be a neighborhood so that you can retract back onto space. An approximate absolute neighborhood retract, you're allowed to move the points down in the space. So the map that sort of sends the neighborhood back into your space is allowed to move the points inside the original space. Whenever I Google AANR, I run into the American Association for Nude Recreation. So that's a little bit confusing. So you can see this was done quite a while ago. And then we had to wait quite a long time for matricial semi-projectivity to be characterized. And this is, I think, was published last year. Tatjana and Dominic Enders worked this out. So I have to start by saying, let's suppose my x is finite dimensional. Then being matricially semi-projective is precisely the same as being no more than two-dimensional, and then having the second cohomology with rational coefficients to vanish. So this thing with dimension strictly less than infinity is a little bit annoying. As you'll see in a second, this is not a problem for groups, so we'll make this go away. But it's possible. This is a fascinating thought. I mean, I don't think you guys believe it exists, right? But it's possible that there is an infinite dimensional space X, which gives you C of X, which is a matricially semi-projective, but that would have to be a really weird space. So it would have no closed subset that has a dimension which is more than 2 and less than infinity. But such spaces exist. I mean, there are some exotic spaces that are infinite dimensional, and all their subspaces have either dimension infinity or 0. So you can construct these spaces. So who knows? What does that do for the commutative case? So Mars and Tatjana and I looked at this fairly recently. So we can work out precisely when you get these three kinds. So if your G is abelian, then it's natural to look at the rank of your G, right? The rank is just the rational dimension of G's tensor Q, so you think of it as a Q vector space. You take the vector space dimension. And it's well known that the covering dimension of G is just the rank of G hat is the rank of G, right? So I need to bound the dimension of my dual space, and I can do this easily with the rank. But it turns out that the rank is not really enough to do these things. So it turns out that being semi-projective is precisely for finite or Z times finite. That's not a lot. Weak semi-projective is torsion or Z times torsion. And matricial semi-projective is precisely rank less than or equal to 1. So let me explain how you see these things, or just maybe outline. So let's do the SP1 first, right? So for the first one, you know, if it's finite or set times finite, then it's sort of clear, right? So that's fairly easy to see. I mean, I could also use the result that I mentioned before, because if it's finite or set times finite, then it's virtually set, right? So virtually free. So that gives me that. So the other way, I found an ancient paper by Turunchik saying that if I have, so it's from the early 80s maybe, I think, which says that if you have a topological group, which is A and R, it needs to be a Lie group, right? So it's like F times T to the something times R to the something times Z to the something. But it's the dual of a discrete set, so it's compact, so you can forget about those. And it's one-dimensional, right? So the dual looks like this. So it has to be this way. So let me jump to matricial semi-projectivity, right? So it's clear that if the rank is less or equal to 1, then the condition in the paper of Anders and Schulman is met, because if the rank is less or equal to 1, then the dimension of the dual is less or equal to 1, and so there's no second cohomology, so nothing to worry about. But it's a little bit surprising, perhaps, that it's rank 1, right? So the result that I'm trying to use here talks about dimension 2, right? So you should think that rank 2 would be okay. But the point is that it's a sort of a standard result that if G hat has, maybe, if the rank of set is 2, then the second cohomology rationally is never 0. So you can find this in Hoffman and Morris. So it's a standard book. So the point is that there's sort of two things going on, right? So there's like a dimension restriction. This is, Marius was sort of talking about this as well, right? This is dimension restriction, and there's an obstruction. And the point is that if your group is abelian, then you cannot reach the max dimension without violating the obstruction problem. So, so there's none of these examples that have rank 2. Okay, so maybe a diagram that I kind of like, right? So it's supposed to be vertically you see the rank, and horizontally you have semi-protective, weak semi-protective, matricial semi-protective. So matricial semi-protective is maybe the one that most of you care about, right? So it's this one that is stability in matrices. And then I have these three symbols. So a check mark means this is always the case, a minus means it's never the case, and a box means it's sometimes the case, right? And so for the 0 dimension, I mean the rank 0 case, right, that's a torsion case. So set mod 2, for instance, is semi-projective. And if you do like dyadic rational sense mod set, this is not semi-projective, right? So there are some rank 0 groups, abelian, that will give you semi-projective C-star algebras, and some which will not. And we've sort of characterized which ones. Now, in the rank 1 case, there are some that will give you semi-projective C-star algebras, for instance, the integers. But if you do the dyadic rationals themselves, which is rank 1, this is not going to be weakly semi-projective. Right. Oh, so I forgot to finish the argument here. So so the middle one, right? So you can see that if you're weakly semi-projective, you need to be matricially semi-projective. So there's only rank 1. But of course, there's many rank 1 groups that are neither torsion, which is, sorry, I'm going to say that again. So sometimes you have rank 0 that will give you torsion groups, and those are all weakly semi-projective. Amongst the rank 1 groups, there are many groups that do not look like this, and what we prove is that they're not weakly semi-projective. And the explanation, I mean, we sort of have a kind of it's easier to see that these are weakly semi-projective, but there's a kind of instruction that says that it's impossible to be weakly semi-projective without looking like this, right? So what you should keep in mind is that group, the dyadic rationals, right? So the dual is like a two solenoid, right? And the two solenoid is not A and R, even though it has the right kind of dimension. So that's the point. And what comes up when you have, like, you know, that group, torsion group, like the dual is the two adics, and that's a nice sort of zero-dimensional thing. And if you're zero-dimensional and metrizable, then you're always A and R. So that sort of explains all of that. But I want you to focus now on the special case of a finitely generated abelian group. And I want to point out that these three concepts, right, restricted to this problem, are the same. Right? So if you have a finitely generated group, then all the rank 1s will be all of 3, all the rank 0s will be all 3, none of the rank 2, none of the rank 3, and so on. So this is a concept that is entirely checked in the finitely generated case by the rank. And what I'm going to spend some time now showing you is that when you go away from the abelian case into the virtually abelian case, this is no longer the case. Right? So we have some interesting examples where these that are rank 2, where this is true and this fails. This is where I'm headed with this. You can also specialize to the abelian and torsion-free case, right? And so there aren't any here, so I get them check marks. But actually the ones that I showed you were already torsion-free. So this is what happens there. Okay, so now I'm done with the abelian case. So you can see, I mean, I mean, nothing much is going on in the finitely generated case, but away from that, these notions are actually quite different. Now, I want to talk about crystallographic groups. So this is a special case of finitely generated and virtually abelian groups. Gave you the definition, but these are really sort of, you know, the way to think about them here is that they're sort of virtually abelian, where the core abelian group is set to the n and it's a maximal normal subgroup. And those you can describe them sort of geometrically, and you can count them, and here are the numbers, right? And I will now tell you how many of these groups are semi-projective. And the answer is 2. And how many of them are weakly semi-projective? The answer is 2. And how many are matricially semi-projective? The answer is 14. So I'm going to take you through how you work this out. And this is a bit of a side to this, but maybe worth explaining. So I want to show you the concept of a non-commutative CW complex, so NCCW. So this is something that we introduced in this old paper from '98 that I mentioned before. I think maybe, I mean, the details of this are perhaps not so interesting, but let me show you what you get for the infinite dihedral group. Right? So infinite dihedral group is I mean, there's 2 line groups, the one that I mentioned that are one-dimensional, right? There's set, and then there's this one. What is C star of this, right? So this is a virtually abelian group. So by Thomas result, this is supposed to be a subhomogeneous C star algebra. And I can draw it for you, right? Because it's fairly easy to show you what it is. You can think of it as interval, matrix valued functions on a unit interval. But at the endpoints, it will be scalar. So I'm just going to write it like this. Right, so these are the functions from the unit interval into the 2x2 matrices, with the additional property that at 0 I get something that is scalar, and at 1 I get something that is scalar. And this, of course, sits inside the 2x2 matrices of C of 0, 1. Right, so this is an example of a subhomogeneous C star algebra that sits inside this. But the point is that you can maybe make a nicer description of this. And this is what the NCCW does for us. So let me point out, before I go any further, that this C-star algebra here is very well studied. As you can see, I mean, this is sort of the universal group of two symmetries. So it's the universal C-star algebra of two symmetries. And that's the same as the universal C-star algebra of two projections. And it's very easy to see that that universal C-star algebra is semi-projective. So this has been known for a very long time that this is the case. So you know, that this gives me the strong form of SP is not surprising. Right? But I want to show you that you can create it as a kind of a repeated construction, which is what I'm showing you up there, right? So a zero-dimensional NCCW is just a finite-dimensional C-star algebra, so that looks like sums of matrices, as we've talked about. A one-dimensional NCCW is then a pullback, right? And it's a pullback like this, so I take C of 0, 1 in F, another finite-dimensional C-star algebra. I take the restriction to the boundary of this set. That's just, you know, F plus F. And then up here I have A0, which is my zero-dimensional NCCW. Right, so a general one-dimensional NCCW is what you can put here using a pullback construction. Right, so the pullback is very easy to describe for C-star algebras. It's just the elements in the direct sum here that get mapped to the same thing. So how would I make this as a pullback this way? Well, I would just take, yes, I can put it here, I will just take the 2 by 2 matrices here, I will take the 2 by 2 matrices here, and here I would take C to the 4. Right, so I take these 4 copies of C, that's a C-star algebra, and then I just place it down in these 4 entries. Right, and the pullback will give me precisely this. But the point is that you can do this again. Right, so you can use, now you have a one-dimensional NCCW, you can create two-dimensional NCCWs, and so on. And we proved in '98 that whenever you have a one-dimensional NCCW, it's going to be semi-projective, the strongest possible form. Whenever you have an NCCW which is where n is bigger than 1, it's not semi-projective, it's actually not even weakly semi-projective, but some of them are matricially semi-projective. For this, you need the n to be less than or equal to 2, and then there's a k-theoretical obstruction, right? So I haven't talked about this yet, but C-star algebras come with k-theory. K-theory for C-star algebras are ordered abelian groups, and so sometimes it makes sense to talk about infinitesimals in those. So this is the concept that, this is how we formulated it back then. So this result is from '98, except for the implication from left to right. We were not able to show that, but Marius has, this is, you know, early stages of this project that Marius was describing this morning. Marius showed, because it's not obvious that this is necessary, because you need to sort of have some ways of detecting that it's necessary. But Marius has developed machinery that shows now that this is if and only if. So that's why I'm mentioning it. This was actually an explicit question in our paper from
Excuse me? So does this actually generalize CW complexes in what way?
Yeah, I mean, so the way you should think about it is that you sort of, first of all, the matrices make them non-commutative, right? So you sort of, they're not super non-commutative, it's sort of limited to matrices. And then just like CW complexes, you create them by gluing over boundaries. And so you sort of, but this is sort of dualized from what you would do in a, so a general, it would have to be a finite CW complex, so there's a finiteness that's built into here, which is not for CW complexes. So proving this is very difficult. We had at the time some special cases like this one and the famous dimension drop algebra, for instance, that my co-authors sort of knew already. And then yeah, it's not a very intuitive proof. But the next part is actually, so taking the full semi-projectivity at dimension 1 to matricial semi-projectivity at dimension 2, this is a little bit of a visual thing, and I want to show you this. So this is really, there's sort of a, I hope you can imagine how this works. So this is based on Lind's theorem that was mentioned by Gunnar on Monday morning. So Lind's theorem says that if you have elements in matrices that are, let's say, self-adjoint, norm 1, and almost commute, then in the usual stability sense, you can make them exactly commute, right? So this means for all epsilon there's a delta, and the delta is not allowed to vary with the matrix size. This was proved to be true by Huash and Lin in 95, something like that. Very complicated proof, but Friis and Rørdam came up with a much nicer proof, and it's sort of intuitive, so let me explain how it works, right? So if you have like two commuting self-adjoints, this is really, by spectral theory, this is really a star homomorphism out of a square, like a standard unit square. So what I want to do is I want to take this star homomorphism and I lift it. And I happen to know that if I have something which is one-dimensional and behaves nicely, then I can always lift. Right? This is the semi-projectivity I know in the one-dimensional case, but you can see my space is two-dimensional. What am I going to do about that? And so the idea of Friis and Rørdam is that you can see that for a space like this, you can punch holes. Right? You can avoid spectral values, so you can do the little triangle here. You can do this in an exact way. So whenever you have a star homomorphism that goes like this, and whenever you fix a number of points in your space, then you can avoid those points without changing anything else. And when you've punched holes in your space, then you can retract onto something one-dimensional without moving the points too much. Right? So this is going to cost you an epsilon. But now you're way up there. So this map here, I can, instead of mapping out of this map, out of this space, I can map out of this space. Right? And it's one-dimensional, so it's semi-projective, so I can lift any map. But if you go through this, diagram, you can see it commutes only up to epsilon. And then, but then if you're careful, you can sort of see whenever you can lift up to any epsilon, you can actually lift exactly. Right, so this is the proof, but of course, it's a proof that works only for a square. But it turns out that you can do this a lot more generally, and this is the basis. I mean, in a sense, so my work with Loring and Peterson, we sort of made baby steps on this, and this has been improved over time. But we had to wait quite a long time until the sort of final version is in the paper of Tatjana and Dominic. But the point is that if you have something two-dimensional, it doesn't have to be a square. But there's a problem, right? And the problem is k-theoretical. And so let me point this out here, right? So I didn't tell you what it means to be an infinitesimal. So an infinitesimal in an ordered abelian group with, say, an order unit is something which is sandwiched between -1 and 1, no matter what I multiply on. Right? So these are elements that are, you cannot make them very big or very small by multiplying any number. Why do I talk about infinitesimals here? Well, there's sort of fairly easy explanation of this. The infinitesimals of a product of matrices will always vanish. You cannot have infinitesimals in something like this. You can have infinitesimals in K0 of something like this, but you cannot have torsion. And then finally, the infinitesimals of K0 of C of x, if x is a two-dimensional space, is precisely the integer cohomology. Right, so if you look at this picture here, and I'm trying to go from here to here and lift it to a map up there. Well, there's a potential obstruction, right? Because if I have some infinitesimals here that are sent not to 0 here, then it's impossible, right? Because the infinitesimals here, if I lift, they will be killed. So when I do this lifting, it's impossible if I have infinitesimals here. Well, that's not entirely true, right? It's impossible if I have infinitesimals here that are not sent to 0. And so if I have infinitesimals that are torsion, then actually automatically they will be killed. So it turns out that the potential problem here is not so much infinitesimals, it's non-torsion infinitesimals. And then this is really what is at the base of the result of, so doing this for arbitrary spaces is very tricky, but it's the base, it's the same idea. And the point is you can do this with NCCWs, right? So you can do this with, not with general C-star algebras, it can be very sort of non-commutative, but if the non-commutativity is built into taking matrices and so on, you can sort of do the same argument. So you should sort of imagine that what you have here is not the continuous functions into the scalars, but into some matrices, right? And then if you're careful, you can do the same kind of thing. So this is why, if there's no sort of obvious obstruction, which would be an infinitesimal getting sent to a non-zero element here, then you can actually do it for the NCCWs. Okay, so this is sort of where all of this comes from. Now, I've talked about the line groups, right? There's only 2 of them, and we've checked that they were semi-projective. Actually, you don't have to use our result, but this is a 1 NCCW, so you could also use the result if you want to. That's a little bit, cart before the horse. But if you go to the wallpaper groups, right, there's 17 of those, then of course the first one is set 2, right? And set 2, as we've seen many, many times, Voigt-Kolesko matrices is not stable, right? So it does not have the matricial semi-productivity condition. But if you go to PG, right, which is the Klein-Bottle group, it is a 2 NCCW. It has no infinitesimals, so it's matricially semi-projective. Right, so I can sort of draw it for you. The dual space, the C-star algebra of it looks like this. I don't know if this is a good drawing. So it's the 2 by 2 valued functions that are identified here and here. And here they have to be scalar. And they're scalar in this way. So what I mean by that is on this boundary, it's not a full 2 by 2 matrix. It looks like this, like over there. But these scalars are sort of twisted around, so they're turned. So when I go from here to here, I sort of do a rotation of the matrices. So it's actually just one circle you're seeing here, right? So one circle that goes like that. But this is a typical NCCW, and what I'm claiming, which of course, it maybe isn't so obvious, but what I'm claiming is you can do this, right? Punch holes, retract, and so on. And at the end of the day, you get a 1 NCCW. Right? This is no longer commutative, it's a 1 NCCW, but we proved that they're all semi-projective. So this is how that goes. Right, so, our starting point was that here's the 17, there are, symmetry groups of patterns like this. So 1 is not good, right, the set 2, and 1 is good. And then we were just thinking, okay, which ones work? And here's the answer. So when you go through, then simply they're all NCCWs, and then you just compute the K0, and you can check if you have any infinitesimals, and in these 12 ones you don't, and if in the remaining 5 you do. There's sort of an explanation, right? It's a better explanation, and this is something about glide reflections. You have some sort of torsion sitting, but this is the way we did it. It was a very sort of ad hoc. I should mention, this is embarrassing. I don't know how to prove that all crystallic graphic group C-star algebras are NCCWs. I think that's true, but I don't know how to prove it. But if you sort of give me a concrete group, I can check it. And actually, I was lucky, or we were lucky, that there was a thesis written in '97 in the University of Saskatchewan, where somebody went through this and checked that they were all NCCWs. So it was done. Right. So here you can see the green ones are matricially semi-projective and the red ones are not. Or like this. Right. So what does this mean to the general question of virtually abelian? right? So one thing that's interesting here, I want to maybe say this first, right? So first of all, if you have a virtually abelian group, it makes sense to talk about the rank. The rank is just the rank of the abelian core, and this is well defined. And also there's a very striking result by Eilers, which characterizes the subhomogeneous C-star algebras that are semi-projective. And it's a little bit difficult to explain, but you sort of look at the spectrum corresponding to the n-dimensional representations. They will be Hausdorff, and they need to be A and Rs. Maybe you need to one-point compactify. But that's not enough. There's sort of a gluing condition. It's a little bit intricate. It's also true that if you have an SP subhomogeneous C-star algebra, it's an inductive limit of these 1n CCWs, but again, it's not enough. You need to know something about the maps being nice. So Marius and Tatjana and I were trying to work out precisely for the virtually abelian groups what happens, right? And this is tricky. So first, let's look at the finitely generated subcase, right? So the finitely generated subcase in the abelian case, rank said it all, right? This was the main observation I had there. This is no longer true, right? So if you have, there's rank 2 groups, some of them will give you something which is matricially semi-projective, and some will give you some that are not, right? So PG and it's called P1 on the other slides. And we can show that in this case, all the rank 1s are semi-projective. That's actually fairly easy, because if you're rank 1 and finitely generated, then you're virtually set. Right? And if you're virtually set, you're virtually free. So done. This is even easier. And we can also show that if we have 3, some of this was actually done in our original paper with Adam, then they're not neither of these nice things. We don't know how to do these, and this is a little bit annoying. If I knew that every such C-star algebra was an NCCW, I could just apply the result that I mentioned before, but we don't. But it's somehow, you know, it seems wrong that you should have something, be able to have something which is, say, weakly semi-projective and rank 2, but we cannot yet rule it out. I mean, I strongly believe that they don't exist. You can also specialize to the torsion-free case. Yeah, I mean, there's not a lot of new things to say here, but the point is that, again, you know, these are actually the 2 Bieberbach groups I have at level 2, right? So they're both torsion-free. So again, this is sometimes true, sometimes not true. And then down here, we can show that this is not the case. We don't know what happens here, and also it's a little bit unclear how to characterize the torsion-free weak semi-projective ones. But we have a nice observation, so that if G is virtually abelian and torsion-free, then if G is SP, then G is Z. It's the only choice. So there's, I mean, we're beginning to sort of see, I'm maybe, don't have a lot of time to say, but I think we're hoping that eventually we'll be able to work out precisely what virtually abelian groups have these properties. And I'll end by saying something very ambitious. As far as I can see, there's nothing to stop us from saying, suppose I have a virtually abelian group, its rank is less than or equal to 2. Now assume that the K-theory of the group C-star algebra has only torsion infinitesimals. Then it could be true that it's matricially semi-projective, right? That would give a lot of new examples. And you would have to prove it by sort of doing the Eilers-Schulman machine with a little bit of non-commutativity. But I think that's not just around the corner. I'll stop here.
Any questions?
So when you're doing the crystallographic thing, you said 1K compute the K theory. How did you guys do
So computing the K-theory of the crystallographic groups, I don't know of a machine for doing it, but you can sort of, I found another thesis where somebody works out, you can sort of, essentially, of course, it's related to group cohomology, and then if you sort of work through these things, you can
Move it
simply...
over to a geometric thing rather than doing C-star?
Yeah,
Okay.
yeah. But you can just sort of describe these K groups in a fairly straightforward way. So when you know that it's an NCCW, you have this gluing process, and then you can compute the K theory by knowing the K theory of the connecting maps.
So it's important that they were in CCW complexes to calculate.
Yeah, and so as soon as it's an NCCW, it's not so hard to compute the K theory and work out if you have the condition. What's mysterious to me is whether or not all groups are NCCW. And the only way I know how to do this for crystallographic groups is that, you just write up the group and you try to guess the structure. So, that's not the right way, and especially when you can ask this question about space groups, right? There's 200 and whatever. So I'm looking at Stuart, so it's like working on these guys, right? It's not so easy to get your hands on these things, but it could be true. I'm not very confident that it is true, but that would be nice.
Is there an intrinsic characterization of NCCWs?
No, that's a part of the problem. Exactly. Yeah. So I think, and maybe, also there's another option, right? And that is that the definition of NCCW is not the right one. Who knows, right? It was made a little bit ad hoc, and I think it's the right one in dimension 1. But yeah.
Any other questions?
I have a question. I don't know, it may be very naive, but I noticed that these properties for Abelian group, they are related with the rank of the group. So, and when the rank is small, then we have these properties. And somehow smaller rank also gives us strict comparison and stuff like
Right.
that. So is there any connection between these properties and strict comparison?
There might very well be. I wouldn't know how to put my finger on it, but that actually might be very interesting. It's sort of recasting this in a more, because all of us, it's all done fairly ad hoc, and there should be, maybe a more systematic way of understanding these things. But I don't know of a precise connection.
Yeah, and other thing, it also may be a very naive question. How these properties behave with other C-star algebraic constructions like inductive limits?
That's a good point. Maybe I should have mentioned that. Not well. So there's very few results. So for instance, you can have inductive limits of things that are semi-projective, does not have to be semi-projective, or even weakly semi-projective.
And I noticed because there is a bound on NCCW complexes for these properties, so
Right.
they don't also well behave with respect to extensions,
Right.
because otherwise
Right.
we'll get higher.
Let me tell you something which is embarrassing. It's unknown if the direct sum of two semi-projective C-star algebras is semi-projective. It's known if they have units or sigma units even. But so there's some really very basic questions in Blackadar's paper from 1985 that remains open. So there's lots of strange things.
Okay, thank you.
Any more questions? Okay, so let's thank the speaker again.